Welcome to this video. I'm going to look at chapter 12 of this special publication of SEG, which is about porphyry deposits associated with alkaline magmatism in Gangdese and Sanjiang metallogenic belts. Okay, let's step back and ask a bigger question. Why do these methods matter for porphyry research in places like Tibet? First of all, it's a huge data compilation. This study brings together more than 850 geochemical analyses and over 2,000 isotope measurements. This scale gives us a bird's eye view of magmatic systems across southern Tibet and western Yunnan. And why does that matter? Because big data sets reveal patterns that small studies simply can't, especially in tectonically messy regions where porphyry systems don't follow the usual arc rules. And the next thing is that whole rock geochemistry, major and trace elements like strontium, yttrium, and lanthanum ytterbium ratios are not just numbers, they are fingerprints. They tell us about the depths of melting, the oxidation state, and the way magma evolved. Those fingerprints help us recognize fertile magmas, the ones that are capable of carrying copper, gold, and molybdenum. Then we have isotope analysis results in this study. Strontium, neodymium, and hafnium isotopes, and they all trace magma's ancestry. Whether it came from the mantle, old crust, or it's a hybrid mix. And we also have zircon isotope studies and results, and their oxygen isotope results, which add another clue showing how much crustal material got stirred in. And why does it matter? Because porphyry fertility depends not just on heat and water, but also on the source of the melt. Isotopes let us read the magma's genetic code, and we also have apatite mineral chemistry. By measuring sulfur, chlorine, and fluorine, the study shows how volatiles behaved inside the melt and when saturation kicked in. That's very critical because volatiles are what drive ore formation. Elevated chlorine and fluorine, along with sulfur zoning in apatite, marked the moment magmas began exsolving metal-rich fluids. They're very trigger for porphyry deposits. And we also have geochronology with uranium, lead, zircon, and rhenium, osmium, molybdenite dating. The study locks down when magmas formed and when mineralization happened. Timing is everything. Linking the right magma pulse to the ore forming event is how we build high confidence exploration models. And finally, spatial and temporal correlation is another key feature in this study. By mapping these chemical and isotope signatures across different terrains, from the Gangdese belt to the Sanjiang region, this study highlights where porphyry potential may still be hidden. Areas with bright chemistry but no known deposits yet. Okay, let's take a closer look at this map of Tibet. What you're seeing here is a tectonic patchwork stitched together by a mosaic of ancient suture zones. But what really grabs our attention, the Cenozoic alkaline volcanic rocks and the surprising number of porphyry, copper, and gold deposits sitting right next to them. Now let's break it down. The Gangdese belt in southern Tibet is home to giants like Kulung and Jiama deposits, and the Sanjiang belt extending into western Yunnan hosts deposits like Biao and Machangking. And there are the Qiangtang and Songpan Gangdese trains, which are less famous, but they're rich in alkaline magmatism and full of untapped potential. Each colored diamond on this map marks volcanic rocks of different ages, from young, bright yellows with less than 10 million years old to ancient deep blues, which are more than 40 million years old. And the triangles, they are porphyry, copper, and gold deposits. And notice how they are not scattered randomly. These spatial overlap between porphyries and alkaline volcanic fields and rocks is not a coincidence, it's a clue. These alignments are fingerprints of or porphyry or forming systems which are still hidden in the crust. And here's the exciting part. Regions like Qiangtang and Sungpan Gangdese remain largely underexplored. But the rocks are speaking, and we have the right potential for untapped deposits. This map shows a tectonic backbone of the southern Tibet. It's a cross-section of suture zones, terrains, and magmatic belts that all formed after the massive India-Asia collision. On the left, you can see the major crustal blocks, the Himalayas to the south, Lhasa terrain in the middle, then Qiangtang, and further north we have Songpan Gangdese. And cutting between them are the great sutures, the Indus, Yarlung, Zangbu, and Bangong, Nujiang, and Jinsha. They are suture zones, and they're not just lines, they're ancient scars from tectonic battles that stitch together Earth's highest plateau. Now let's zoom in on the southern Lhasa terrain. This is where the real action unfolds. We see belts of adachite-like high strontium yttrium granitoids in yellow, born from melting of thickened lower crust. The ultrapotassic and schistotic rocks in purple. And they came from mantle-derived melts loaded with volatiles. And we have Linzizong volcanic succession in gray, which preserves the earlier story of subduction magmatism. And then there are the red hammer symbols. Each one marks a porphyry copper deposit, like Kulung, Lima, Juno, and more. Together they tell us that this is not a typical arc system. Unlike classic porphyry systems that form above subducting slabs, these deposits belong to a post-collisional world long after subduction ended. And here's the recipe. Mantle melts rise upward, hitting and melting the thickened lower crust, which creates high strontium yttrium granitoids, hydrous, volatile-rich, and capable of carrying metals. And at the same time, ultrapotassic dikes intrude, adding more heat, more fluids, and driving copper, gold, molybdenum into the upper crust. Notice how deposits tend to cluster where granitoids and ultrapotassic rocks overlap. And but there are also places to the far east and west where these magmatic rocks exist without any known mineralization. Those zones stand out as high potential targets for the next wave of exploration. Here is a big picture, the Sanjiang region in southwest China. This corridor stretches across western Yunnan into eastern Tibet, and it's a geological crossroads where continental collisions and post-collisional magmatism shaped the crust. For explorers, this is one of Asia's most intriguing frontiers. Now let's decode the tectonic framework. Multiple suture zones, Sanjiang, Eilao-shan, Bangong Nujiang, they all mark the scars of ancient ocean closures. And we have arc-related volcanic belts like Jiadu Jingong and Zhongdawixi, which carve their way across the region. And right where these deep structures cut the crust, clusters of porphyry, copper, gold, molybdenum deposits appear with standout names like Yulong, Malasongdu, Machanking, and Biao. Each deposit is anchored by precise age data from zircon dating, molybdenite dating, and the pattern is striking. Two key pulses of mineralization are recognized in this region. One between 40 to 35 million years ago, and another between 36 to 33 million years ago. And these were not random events, but episodic. They are linked to crustal shortening and major strike-slip faulting. So why does this map matter to explorers? Because it shows how Cenozoic alkaline intrusions, crustal scale faults, and porphyry systems connect, even outside traditional arc settings. This challenges the old paradigm. Porphyry systems don't always require an active subducting slab. Instead, fertile mantle melts, a thickened crust, and deep translithospheric faults can drive ore formation. Here's the exploration takeaway from this picture. Deposits like Dujiashongdu, Yulong, and Biao, they all align along the Eilao-shan Red River Fault. These structures acted like vertical highways, channeling metal-rich magmas to the surface. And the blank areas on the map with the same rocks and the same structures but no known deposits yet, they represent untapped frontiers. Let's break down these four geochemical plots because they show they give us a lot about magmas that fueled porphyry copper gold systems in southeast, southwest China and Tibet. Starting with the total alkali silica diagram, where we plot sodium plus potassium against silica. Most samples cluster in the trachyandesite to trachyandesite fields, with some extending into rhyolite and granite. These patterns point to evolved alkali-rich magmas. They're not the simple arc magmas we would expect. Instead, they have interacted with the crust. They're volta-rich, and that's exactly the kind of chemistry linked to porphyry fertility. Next, we have potassium versus silica diagram. Here we track how potassium evolves as silica content increases. Most samples fall into the high potassium, calc-alkaline, and shoshonitic regions. These are signatures of crust-influenced, metal-enriched magmas. High potassium content also signals higher fluid saturation, elevated temperatures, and greater capacity to carry metals upward into ore forming system. Now look at the potassium versus magnesium diagram. This one highlights ultrapotassic rocks defined by potassium greater than 3% and magnesium oxide greater than 3%. These are mantle derived, only lightly fractionated, and extremely fertile. They're hot, volatile charged, and strong enough to partially melt the crust. Many samples from the Lhasa volcanic suit, Western Yunnan, and even Yulong sit squarely in this fertile zone. Finally, we have potassium versus sodium diagram. This separates calc-alkaline, schistotic, and ultrapotassic fields. Suits like Lhasa, Yunnan, and Yulong consistently fall in the schistotic to ultrapotassic range. That points to metasomatized mantle sources, magmas that hybridize with crustal melts, and created ideal conditions for porphyry mineralization. The bigger picture here is unmistakable. These geochemical fingerprints prove that the Sanjiang and Lhasa magmas were not produced in a classic subduction arc. Instead, they formed in a post-collisional setting under crustal thickening and strike-slip motion. And the real drivers were ultrapotassic melts, not passive background magmas, but there are engines that delivered heat, volatiles, and metals into the upper crust. So these porphyry systems are not arc-borne, they're collision-borne, mantle-fueled, and their chemistry tells the story with a remarkable clarity here. This diagram tracks the evolution of hafnium isotopes in zircon crystals from Cenozoic magmatic suits across Tibet and Yunnan, and they are plotted against their crystallization ages. On the vertical axis, we have hafnium values represents the isotopic fingerprint of the magma source. Values above the core line, CHUR line, point to juvenile mantle-derived melts, while values below indicate reworking of older continental crusts. And the horizontal axis shows ages from present back to about 80 million years ago, capturing major magmatic pulses that followed India-Asia collision. And looking at the data by suit, it shows a striking contrasts. We have suit 1, which is the alkaline volcanic rocks in Lhasa terrain, and it shows mostly negative hafnium values, which is a strong signal of crustal reworking from ancient basement. In suit 2, we have Miocene granitoids of Gangdese build. They stand out with dominantly positive hafnium values, reflecting juvenile mantle-like input, and the kind of fertile magmas most often linked to porphyry copper systems. We have suit 3, which are alkaline volcanics in Western Yunnan. It plots in the middle ground, mixing mantle and crustal sources. We have suit 4, which are granitoids of Western Yunnan. They show mostly negative to slightly evolved hafnium values, pointing toward partial crustal derivation. We have suit 5, alkaline volcanic rocks in the Yulong porphyry belt, span a broad range but trend toward crustal values, suggesting reactivated lithosphere. We have, and finally, suit 6, which are granitoids in the Yulong porphyry belt, They cluster in mildly negative hafnium space with limited mantle contribution. Inherited zircons shown in gray carry isotopic signatures from Proterozoic crust recycled into younger magmas. Their presence highlights the deep involvement of ancient crust in many of these systems. And the interpretation is clear. The Gangdese granitoids are the isotopically fertile suit. They are mantle-derived, they are juvenile and potentially oxidized, making them strong candidates for porphyry copper generation. In contrast, magmas from the Lhasa terrain are largely crustal and on their own less likely to generate porphyries, though they may help trigger melting when mixed with mantle-derived inputs. Juvenile hafnium values often indicate magmas that are metal-rich and volatile bearing. Negative crustal hafnium signatures point to recycled, evolved sources that may be less capable of driving large ore systems. The bigger takeaway is that hafnium isotopes are more than a timekeeper. They are a tracer of magmatic potential. In post-collisional belts like Tibet, targeting magmas with positive hafnium during the key magmatic pulses can help explorers focus on the most promising porphyry systems. So hafnium doesn't just tell us when magmas formed, it tells us where they came from and whether they had the right ingredients to build a porphyry giant. These plots show the chemical signatures of magmas from two key regions, the Lhasa terrain and the Gangdese belt, shown in green and red. And we have Western Yunnan shown in blue and orange. Starting with the Lhasa and Gangdese suits, the alkaline volcanics of Lhasa show strong enrichment in LRE, light rare earth elements, while the Miocene granitoids of the Gangdese belt display even steeper RE slopes. These are classic signs of evolved crustally influenced melts. A key feature is the deeper europium anomalies in the Gangdese granitoids, which reflect plagioclase fractionation during magma evolution. In the multi-element plot, the Gangdese suit also shows strong spikes in thorium, uranium, potassium, and lead, which are clear fingerprints of fluid addition or crustal contamination. And they vary processes that enhance porphyry fertility. Turning to Western Yunnan, both alkaline volcanics and granitoids show more subdued signatures. Their RE profiles show moderate LRE enrichment with weaker europium anomalies and relatively flat HRE segments. That flatness points to garnet in the residue, which is suggesting the melts occurred at depths beneath thickened crust. In the multi-element patterns, both suits show negative niobium and tantalum anomalies paired with lead enrichment, which is consistent with the subduction modified mantle source, the one which is enriched, oxidized, and potentially metal bearing. The overall message is clear. These geochemical fingerprints highlight magmas that were evolved through crustal assimilation, and they are enriched by fluids and in several cases tapped into high pressure garnet bearing sources. And together they define the fertile conditions necessary for building large porphyry copper systems across Tibet and Yunnan. Here we have the Yulong porphyry copper belt results, which is represented by suits 5 and 6. It shows a distinctive chemical fingerprint. Both the volcanic and granitoid rocks show steep enrichment in LRAE, with relatively flat patterns across the middle to HRAE. This smooth shape suggests evolved crustal influenced magmas that retain their fertility potential. In the multi-element diagrams, several unique signals stand out. We have niobium and tantalum, which are strongly depleted, and they're producing pronounced troughs. This pattern is typical of subduction modified sources, yet here it occurs in a post-collisional setting. At the same time, thorium and uranium remain consistently elevated, which is a clear marker of fluid mobile element enrichment. Together, these features point to magmas that were charged with both metals and volatiles. When paired with hafnium and strontium neodymium isotope evidence, the picture becomes clearer. These rocks represent hybrid cross-mantle magmas, mixing deep juvenile inputs with reworked lithosphere. The result was a fertile environment primed to generate porphyry copper systems. And the key takeaway is that even outside of subduction zone, these magmas developed all the classic fertility indicators: high enrichment in LRE, europium anomalies, which link to plagioclase fractionation, niobium tantalum depletions, thorium uranium peaks, and signatures of garnet stable melting depths. And these are all chemical hallmarks of porphyry potential, and they're not forged not by ongoing subduction but by post-collisional tectonics driving mantle crust interaction. This figure shows how apatite minerals from the Kulung and Yanying intrusions capture the volatile and oxidation history of porphyry forming magmas. Starting with sulfur, the SO3 contents of apatite are often used to estimate the oxidation state and sulfur capacity of the magmas. In this case, porphyry hosted apatites show only moderate values, typically around 0.1 to 0.2 weight percent. They're similar to more mafic samples from RMCL soot. Higher values above 0.5 weight percent occur mainly in the trachyte and monzonite apatites and are concentrated in ring compositions. This suggests that sulfur enrichment was a late-stage process tied to volatile buildup during final crystallization rather than early magma evolution. Fullerene contents tell us a different story. Porphyry apatites usually hold elevated fullerene contents, somewhere between 3 to 3.5 weight percent, significantly higher than the RMCL and monzonite samples. The trachyte soot reaches even higher values, approaches 3.7 weight percent, which is a signal of extreme magmatic evolution and fractionation. Fullerene here is a robust proxy for volatile-rich evolved melts and supports the idea that porphyry systems retained significant volatile budgets early in their development. Fullerene provides another clue. Porphyry apatites contain between 0.35 and 0.55 weight% chlorine, which remain below 0.3%, and far above the RMCL values. This enrichment points directly to incipient fluid saturation, the critical step that allows copper and molybdenum to be mobilized in porphyry systems. The elemental map of apatite zoning captures the process visually. The core of the crystal is poor in sulfur, the mantle zone shows moderate enrichment, and the rim records values as high as 0.8 weight%. This concentric pattern documents progressive sulfur enrichment, likely caused by volatile exsolution just before ore-forming hydrothermal activity began. The broader insight is that sulfur alone is not always the best fertility predictor. Instead, we have chlorine and fluorine concentrations combined with zoning textures give a far clearer picture of volatile evolution and the magmatic to hydrothermal transition, which is quite necessary in porphyry mineralization. Here we have a histograms of geochronological results. Let's start with the Gangdese belt in southern Tibet. The histogram shows the age distribution of two key magmatic suits. We have Miocene granitoids and Cenozoic alkaline volcanic rocks. The average age of porphyry, copper, and molybdenum deposits is about 16 million years, which aligns almost perfectly with the peak of Miocene granitoid emplacement. This close match suggests that these intrusions were directly responsible for mineralization. Moving to western Yunnan, part of the Sanjiang metallogenic belt, the data show a slightly different story. Here the porphyry deposits average 36 million years, and the granitoids cluster tightly around that same age, while the volcanic rocks peak slightly later. This points to porphyry mineralization being closely tied to granitoid emplacement, with volcanism perhaps making the waning stages of magmatic activity or late fluid release. In the Yulong porphyry belt of eastern Tibet, one of the richest copper belts in China, the average deposit age is 41 million years. Both volcanic and granitoid suits overlap with this timing, but the spread is broader. And this suggests that multiple pulses of magmatism contributed to ore-forming conditions, with recurrent mantle inputs or crustal recharge sustaining fertility over a longer window. Across all these regions, a consistent pattern emerges, which is porphyry mineralization is synchronous with or slightly later than major magmatic pulses, especially high potassium oxidase and volatile rich granitoids. In the Gangdese, deposits align with Miocene intrusions around 16 million years. In western Yunnan, they cluster at 36 million years. And in the Yulong belt, they span a broader magmatic hydrothermal system centered in around 41 million years. For explorers, this timing is critical. If your magmas don't fall within the original porphyry ore window, the system may not be fertile. If it's too early, the melts are primitive, volatile-rich, and unfocused. The raw ingredients are there, but the recipe is not ready to cook. And if it's too late, the system is degassed, crystallized, or already eroded, like arriving after the party has already ended. But if the timing is just right, the magmas are fertile, they're hydrous, fluid saturated, with pressure conditions ideal for driving hydrothermal circulation and or formation. In this window, the geochemical fingerprints align with apatites enriched in chlorine and fluorine, zircons recording high hafnium values, and the whole rock geochemical data shows elevated strontium yttrium and lanthanum ytterbium ratios. These are the markers of a system primed to generate giant porphyry copper deposits. Here we have in the first panel zirconium concentration plotted against silica. Zirconium decreases steadily as silica increases, which is a classic signal of zircon saturation and fractionation. The highest zirconium values, especially in the Lhasa and Western Yunnan volcanic suits, reflect hotter, less evolved melts crystallizing early. In contrast, the ore-forming Miocene granitoids of the Gangdese belt and Yulong granitoids cluster at much lower zircon contents but higher silica, which is consistent with extensive zircon fractionation. This shift marks a crucial fertility filter. Magmas need to reach zircon saturation before volatiles can begin to concentrate and separate into ore-forming fluids. In the second panel brings in temperature using zircon solubility models to calculate zirconium saturation temperatures. The fertile granitoids from Gangdese and Yulong record unusually high saturation temperatures in the range of 750 to 900 degrees Celsius, even at evolved silica contents. And that is hotter than expected for these compositions. And the significance is clear. High temperature, evolved magmas can store more water and volatiles. They can remain fluid for longer periods and sustain the conditions necessary for porphyry formation. In other words, they're not just oxidized melts, but superheated and pressurized magmas. In the third panel, we have dysprosium ytterbium ratios plotted against silica, which is a high potential and a powerful tracer of mineral fractionation at depths. Many fertile samples maintain dysprosium and ytterbium ratios above 2, even at high silica contents of 65 to 75%. This pattern indicates garnet and amphibole involvement, minerals which are preferentially retain middle rare earths while depleting the heavy ones. Such behavior is tied to high pressure evolution in a thickened crust and helps explain the elevated strontium yttrium ratios that are widely recognized as porphyry fertility indicators. The fourth panel expands this view by mapping out mineral fractionation trends. Garnet fractionation drives dysprosium ytterbium ratios upward with little change in silica. Amphibole fractionation pulls dysprosium ytterbium downward as silica rises. differentiation troughs, crustal melting moves compositions rightward, which indicates indicating silica without strongly affecting dysprosium and ytterbium. Most porphyry-related samples fall in the intermediate space between garnet and amphibole, which is suggesting a mixed control. And this supports a model where mantle-derived magmas intrude into thick lower crust, and they trigger partial melting and interact with garnet and amphibole-bearing lithologies to generate fertile hybrid melts. Taken together, these plots show that porphyry-forming magmas in the Tibet were unusually hot. They were volta-rich and deeply pressured. They crossed the zircon saturation threshold, evolved under high pressure with garnet and amphibole fractionation, and retained enough heat and voltage to power long-lived hydrothermal systems. Zircon geochemistry and rare earth element ratios can give us a mineralogical roadmap, one that explains how post-collisional magmas evolve into porphyry genes, even in the absence of an active subduction zone. Here, the map that we have how alkaline magmas build porphyry giants in this area, some cartoons. In the Gangdese belt of southern Tibet, subduction was steep. The Indian slab, dove dive, went deep into the mantle, forcing hot asthenospheric upward. Hydrous alkaline magmas rose through the crust, but instead of erupting at the surface, they stalled in the Tibetan middle crust. Their old arc cumulates, rich in sulfides and melts, were remelted, and this process recycled copper and sulfur, feeding the generation of high strontium yttrium granitoids. These magmas, pressured and volta-rich, built fertile porphyry systems such as Kulung, which is one of the largest in Tibet. Going to the right, shifting to the Yulong belt, tectonic picture changes. By this time, subduction had ceased. Instead, the lower lithosphere detached and sank, allowing a convective upwelling of hot asthenosphere. Alkaline magmas ascended, melting thickened lower crust that had been enriched by earlier subduction events. And the result was the emplacement of high potassium, high strontium yttrium granitoids saturated with water, sulfur, and metals. And here the crust itself became the principal source of copper and gold, producing some of the richest porphyry deposits in China. And in the far right, Western Yunnan, the setting was different again. This region sits on the edge of the Gangdese craton, far from any active subduction. Hydrous mafic alkaline magmas rose from ancient subcontinental lithospheric mantle. When these magmas intruded into the lower crust, they melted garnet and amphibole-bearing lithologies. The outcome was oxidized, water-rich granitoids that powered enormous porphyry and skarn systems like Biao, which is famous for its gold, copper, and polymetallic endowment. Together, these three case studies show that porphyry systems in Tibet and Yunnan were not products of a single tectonic cycle. In the Gangdese, they were born from subduction recycling. In Yulong, they formed from lithospheric removal and crustal melting. And in Western Yunnan, they form from craton margin magmatism. Different geodynamic genes here, yet converging on the same result, which is fertile, volatile saturated magmas capable of producing big porphyry systems. As we wrap up, it's time to rethink the rules of porphyry exploration. Not all world-class deposits form in classic arc settings. The Gangdese, Huang, and Western Yunnan belts prove that post-subduction, post-collisional, and intraplate environments can also generate fertile porphyry systems. And what's the secret ingredient? Alkaline magmatism. These magmas are not just hot, they are oxidized, hydrous, and rich in sulfur and chlorine. And when they interact with thickened or previously metasomatized crust, they unlock deep metal reservoirs. And here timing is everything. If your magmas are too early, they are dry and unfocused. Too late, the system's already degassed and eroded. And the sweet spot is high strontium yttrium, fluid saturated melts that are still under pressure. These fertile conditions often appear near lamp porphyries and schuschonitic intrusions. So watch for them in your exploration programs. The big takeaway here is that expand your exploration lens. Arc signatures are not the only path to porphyry giants. Look for right geochemistry, right pressure, and also the crustal content. Thanks for watching.